Hi everyone, and welcome to our video on electric charge. So we'll learn a little bit about lightning and how that works. We'll learn a little bit about why electrons are and atoms are an important part of electric charge. So let's dive into what I'm looking for you guys to understand in this lesson. So I want you to be able to explain and draw models of charge, where it comes from, and its implications. And here are some success criteria. So can you explain and draw a model of atoms with positive and negative charge? Can you explain how charge moves from one object to another? Can you explain how materials are affected by charge? And can you explain and draw models of shocks and lightning? So electrostatics is usually where a lot of textbooks start, and really that's just the idea of something having charge and that charge is being held in one place. So charged objects that either means like you've lost some electrons or you've gained some electrons. And some objects might gain electrons, some might lose them, but overall the charge is conserved. So just like last quarter when we talked about how energy is conserved, one important rule is that charge is conserved. So if some electrons move from one object to another, however many electrons moved, so you're going to have some negative charge, and then the other object will have some positive charge. You might have seen this in the activity that we do in class where you had to rub some objects and maybe some gained electrons. Whatever electrons they gained had to come from another object. So the charge overall is conserved. So what are electrons? So you might have seen like a model that looks like this. So this is a typical model for how atoms are shown. And so there's protons and neutrons in the middle, and then there's electrons that kind of orbit around. Now, what's really happening is much more complicated, but this is a good model for us to kind of think about what an atom looks like. Another model is something called the Bohr model, named after Niels Bohr, a famous scientist. And his model looks like this, where you have the electrons in certain orbits. And you might have 2 electrons in the first orbit, and then you can have up to 8 electrons in the next orbit. This one only has 5 because nitrogen only has a total of 7 electrons. And so we can have these electron orbits, we have electrons floating around, and protons and neutrons are in the middle. Some important rules about atoms. So atoms are made of 3 subatomic particles, protons, neutrons, and electrons. Usually atoms have the same number of protons and electrons, and electrons are negatively charged. And electrons are able to move, while the things in the middle of the nucleus, the protons and the neutrons, don't really go anywhere. So when we look at this model, again, the electrons are on the outside and they're able to move from one atom to another. Sometimes that's how chemical bonds are formed. It's all about like what the electrons can do. So because we have these electrons and they're able to move, that's how we get charge. We get electrons to actually move, and that can lead to an electrical current. And so there are some objects that are really good conductors of electricity. So steel, silver, gold, even seawater and copper, those are really good conductors. So conductors are able to move a charge really well. They often have a free electron. So when you look at those orbits around the nucleus of an atom, there's usually one electron that's kind of just free and it's able to move, and that usually means that that object will be a good conductor. Copper is a great conductor, and this is why it's often used in electrical systems. And if you looked at the model of copper, it's a lot of electrons, but if you'll notice, the key one is here. There's a single electron in the outer orbit. So that electron is kind of the free electron, and it's able to move. And because that electron is able to move, that's what we actually get, like a current. We actually get electricity to flow because the electron is able to move easily. So when you look at the periodic table, and I might just highlight a few things here. So when you look at this area here, we have copper, but we also have silver and we have gold. Those were 3 really good conductors. Notice that they're all right down this column of the periodic table. So I know many of you haven't taken chemistry, but one rule you should know about the periodic table is these are all the elements in our world, in our universe, as far as we know. And a lot of the ones in the same column have the same properties. So all these ones have very similar properties. And one property they have in common is that they're all very good conductors. Oops, didn't mean to do that. All right, so insulators are like the opposite of a conductor. So insulators do not conduct electricity very well. They can gain or lose electrons, but the electrons don't easily move. Rubber is a great insulator. So this is why we often wrap our copper electrical wires with rubber so we don't get shocked. And so when we look at an insulator, that means the electrons won't flow and we won't get an electrical device to turn on. So rubber, oil, plastic, glass, these are all things that are not good conductors. And we call them insulators. So speaking of getting shocked, so electrical shocks can be very dangerous. It depends on how much power there is and how much current is flowing. So we definitely don't want to touch an outlet. That's why you might have heard that from a very young age. So shocks can occur when electrons quickly move from one object to another. So when electrons move from one object to another, there could be like a lot of electrons, there could be just a few electrons, and so we can see various amounts of shock depending on what happens here. So outlets are bad, but you might have seen situations where like you rub your feet on carpet and then you touch a metal doorknob and you get a little shock. It will tingle for sure, but it won't kill you. Um, so those are some examples that I put right there on the screen. And so there's a simulation that I'm going to have you guys play around with if you haven't played around with it yet. So there's a simulation where you have to kind of have the electrons build up on a person's body, and then you have to see what they do. But just a short idea is that the doorknobs that we usually see are metal, and so they're good conductors. And so they'll easily have electrons move from one thing to another. All right, and then lightning. So you might have heard of this guy, Ben Franklin, kind of a big deal. He's on the $100 bill. And lightning is just a giant spark of electricity. So let's kind of look at how that works. So Ben Franklin developed many ideas around electricity, and he showed lightning was really the same as electricity and like an electric spark. And I have a should do assignment on that where there's a couple of videos that are very interesting and kind of debunk some of the myths around Ben Franklin and his whole like kite experiment. If you haven't heard about that, check out my should do assignment. Um, and so the basic idea is that negative charges build up on the bottom of clouds, and these charges are attracted to the ground. And so this is kind of a good picture of this. We have like this negative charge, like negative charged molecules are on the bottom of the cloud, and then that kind of means that there's going to be a positive charge that kind of develops on the ground. And eventually, as the charge kind of builds up, there'll be eventually like a spark across the air all the way down to the ground. So it's really just a giant spark of electricity. Now, we all know I think it can be very dangerous. And there's a few things that people do to kind of protect themselves and protect their buildings from lightning strikes. One of the most common things, and one thing that Ben Franklin actually invented, was the lightning rod. So the lightning rod is an idea where you take a piece of light or a piece of metal, and if it gets hit by lightning, that electricity will flow down some metal around your building and then to the ground. And that way, it won't hurt anybody in the building. It won't hurt anything inside the building. You can imagine that there might be some metal objects that we don't want electricity flowing through in our building. So a lightning rod makes the electricity kind of flow around the building, but not into the building. All right, so I hope this was useful, and good luck with the rest of the lesson.